Hello, it's JM from Excellence Tutorials, and in this video we are going to solve some chemistry, and that is under chemical equilibrium. So we have the first question. We get started. Suppose the reaction has the equilibrium constant, that is K is equal to 1.3 times 10 power 8. So this is times 10 to the power 8. So it's not necessarily 1008, but it's 10 to the power 8. What does the magnitude of this constant tell you about the relative concentrations of products and reactants that will be present once equilibrium is reached? So here we have to know that for, let's say, a reaction A plus B equal to C plus D, of course, with some stoichiometric coefficients. For this reaction, we know that the equilibrium constant is going to be the concentration of C to the power C times the concentration of D to the power D over the concentration of A to the power A times the concentration of B to the power B. That's how we get the constant. So if the equilibrium constant, like the value of this, if it's too large, it shows that the concentration of products is far greater than the concentration of reactants. And also that the concentration of reactants is smaller than that of products. Because if the concentration of reactants is larger than that of products, then the equilibrium constant is supposed to be very small. So in this case, 1.3 times 10 to the power 8 as the value of K shows that the concentration of products is larger than that of the concentration of reactants. So what we're saying is that the relative concentration of reactants, that there is, or shows that the product, or the, so it shows that the concentration, shows that the concentration of products is larger than the concentration of products of reactants. Okay, so now the also question, is this reaction likely to be a good source of the product? So the answer is yes, this is a good source of products. Why? Because at the equilibrium point, we have more products than reactants. So it's a reaction whereby you put in little, yet gaining so much. So you put in little reactants, but you have more products. Okay, so we can go to question 2. Question 2 says, write the equilibrium expression K for each of the following gas phase reactants. So the equilibrium concentrations can be written in two ways. One, by using concentrations, and two, by using partial pressures. That is on for gaseous phase. So like in this case, these are all gaseous phase. We can write both, but if the other one is in aqueous phase, we cannot write the what is for partial pressures. So the equilibrium expression for this, that will be K is equal to, so we go to the product, we have NO and then times O2. So you end there. That's the value of the equilibrium concentration. So this is Kc because we're considering concentrations. So for partial pressures, it will be Kp equal to, so the same, so partial pressure of nitrogen monoxide, this one is square over partial pressure of nitrogen times partial pressure of oxygen. So it's as simple as that. We go to B, so we'll be doing the same. So we get for partial pressure and concentration, So for concentrations, this one is going to be Kc is equal to, so we have the concentration of nitrogen dioxide to the power 2 over the concentration of dinitrogen tetroxide. That. So, and our Kp here is going to be partial pressure of nitrogen dioxide squared over partial pressure of dinitrogen tetroxide. So it's that simple. Your pen or pencil, whatever you're using, just going through like just smooth, you know. Don't take school hard. School is easy. So the next question here that we have is this one. Yeah. So I think this one I'm going to give you as an exercise. So you take, you pause this video and take 10 seconds. You do that. So as I wait for you. All right, so hope you did it. So your answers, you can confirm them. They should have been like this. Kc is equal to, we have the concentration of Ci times the concentration of H2 to the SiH4 times the concentration of Cl2 squared. Let me just write this one clearly. I want to see you trying to see SI like that. And your Kp as simple as that. So since everything is in gaseous state, remember, that's the reason why we can get the Kp. Without gaseous state, we couldn't have been doing that. Could have just been getting the Kc for all cases. So this is going to be the partial pressure of SiCl4 times partial pressure of H2 squared over partial pressure of SiH4 times partial pressure of Cl2 squared. As simple as that. I'm sure you got them. So if you did, congrats. Let's go to question 3. Remember that school is easy, so don't complicate it. Now the next question is, given that at the temperature of T, the equilibrium constant for reaction is 1.3 times 10 power negative 2 for this reaction here. Okay, so let me put the reversible signs there. Okay. Okay, so we do this and that. Okay, obviously you're able to see. So now, for this reaction, we are told to calculate the values of K for the following reaction at the same temperature. So we know that for this reaction, Kc is given by what? So it's given by ammonia, that's NH3 gas concentrations and hydrogen gas concentration to the power 3. So like that. So now when we have, and this is the one that is giving us 1.3 times 10 power negative 2 times 10 power negative 2, like that there. Okay, so now get 1.3 times 10. Okay. So now when we get the first one, and so it's not clear there, this is supposed to be 1/2. So this 1/2 this side, and this is 3/2. Yeah, and that's why this just 2. So this 1/2 N2 and 3/2 H2, giving us that. So now we're going to say, for this reaction, the Kc is equal to what? So the Kc is equal to NH3 to the power of nitrogen gas, then the concentration of hydrogen, the power 3/2. Now, if you take a look at what we're doing previously, this was to the power 2. Now the power of 2 has become 1, and here this was just what? This was just 1, and now it has become 1/2, and this was just 3 here. It has become 3/2, which means that this one is coming here as 2/2. So we can clearly see that we're multiplying all powers by half. So which means that here we have the concentration of NH3 to the power N2, and then the concentration of H2 to the power 3, then we're multiplying everything by half, because this 2 times half there is going to give us 1, and 3 times half is 3/2. Then 1 times half is half. So that's how these come, which means that here we're having, remember what is inside here is our Kc. So this is just the Kc to the power half, which means we just have the square root of Kc, and that is the square root of 1.3 times 10 power negative 2. So we have 1.3 times 10 power negative 2 in its square root. This gives us 0.114. So this is the Kc. So it's simply 0.114. As simple as that. So let's go to the next question, which says we have 2 NH3 gas plus into gas, so everything gaseous. So if you take a look at this reaction, it's actually the same as that one in the main question. Yeah, the only thing that has happened here is reversing. They have reversed this reaction. The reaction wasn't like this, but now they have taken the products to be reactants and reactants to be products. So because it's having the same values, that is for ammonia, we had a 2 there in the main reaction, as you can see. So it's the same one that we have there. So and it's the only stoichiometric coefficient that we have, and as well as 3. I mean, okay. So it's just the same, just a reverse. So for a reverse reaction, the constant is Kr. So R is representing reversible reaction for the reverse. I mean, so Kr is equal to 1 over the constant, the equilibrium constant of the forward reaction, which is 1 over, in this case, it's 1.3 times 10 power negative 2. And that's going to give us what? So we have 1.3 exponent negative 2, and then 1 divided by ans. So that gives us 76.9. So it's going to give us 76.9. So that will be the constant, the equilibrium constant of that reaction. And we have yet another reaction. So I'm going to give you this one as an exercise based on the 2 questions we have solved already. Try solving this within 3 minutes. So to say 3 minutes, I think is okay. Yeah, so you can just pause the video and solve. Okay, so welcome back. We finish up this question. So what's happening here is that the Kc in this to the power 4 to the power 2. So remember the original. So in the and then we had H3 times 10 power negative 2. Now then, what is happening so you have to connect 4 and 2. You connect 2 and 1. You connect 6 and 3. And there has to be a constant number that is multiplying everything. We can't be like here multiplied by 2, then there are other numbers. It has to be a constant number. So from 2 to 4, it means we multiply by 2. And 1 to 2, it means we multiply by 2 again. From 3 to 6, it means we multiply by 2. So all these are being multiplied by 2. Hence, we can write this as NH3, N2, and then H2 to the power 3, and then everything to the power 2. So that 2 times 2 is 4. 2 times 1 is 2. 2 times 3 is 6. So this means that we have Kc 3 times 10 power negative 2 in brackets squared. So what is that? So 1.3 exponent negative 2, and then squaring this. So it gives us something like 1.6. So that's the value of the Kp. So in case you'd be wondering what are the units, we haven't been putting units anywhere. All right, so the constant, the equilibrium constant of any reaction is dimensionless. It's a dimensionless constant. It has no units. That's what I mean. That's why I haven't talked of any units here. Okay, so welcome to question 4. I hope you're ready or you're not tired. Some of us are used to these things. we rarely get tired. We get tired when we are done, not on the job. So so we are forced to, or rather we are moved to work out this question. So at a particular temperature, a 2.0 liter flask at equilibrium contains 2.80 times 10 power negative 4, that's power, nitrogen, 2.50 times 10 power negative 5 more oxygen, and all other, those other watts. So there is a question to say, calculate the K for at this temperature for the reaction. So this is the reaction we have now to get the what is the equilibrium constant, because in this case we have been given number of moles, and there's 2 liter flask there, which means that we have everything that we need for us to calculate the molarities or other concentrations. So we're going to solve the K for this reaction using concentrations. So how do we get concentrations? So the concentration of N2 is equal to, since N2 has that number of moles, so it's always number of moles over liters of solution. So the number of moles of solute, so in this case the solute is N2 and it has 2 more as the number of moles, so we divide this by 2 liters, and that's going to give us 2 into 2 times 10 power negative 4 M. So we put M, which is molarity. Then now we also have O2, write it down like how we do it. So everything is going to be divided by 2, because that's how much that flask is, 2 liters. So the next number is 2.00 times 10 power negative 2, again over 2, which is going to be 1.00 times 10 power negative. Dinitrogen monoxide, the concentration of this is going to be what? Times 10 power negative 2 N. So you can make that correction, because for oxygen we have 2.5 times 10 power negative 5 moles. So because of that, 2.5 times 10 power negative 5. Okay, so now we get the case, Kc. So Kc is going to be, from this reaction, we have concentration of the nitrogen monoxide squared over the concentration of nitrogen gas squared, multiplied by the concentration of oxygen squared, which is negative 2 squared over, this is 1.4 times 10 power negative 4 squared, multiply this by 1.25 times 10 power negative 5. And that's going to give us what? So it's 1.4 exponent negative 4 equals squared equals, we multiply this by open bracket 1.25 exponent negative 5 close bracket. So that gives us 245. Okay, let me just write it so that in case you have time, just find the answer. Power negative 13. And then on the numerator, we have 1.00 exponent negative 2, then squared. So this is the same 1.00 times 10 power negative 4. So that divided by 2.45 exponent negative 13. What is it going to give us? So it's going to give us 408.15.3. So it's 408,163,265.3 dimensions. So they are no units. Though I almost said kwacha because that's so much money. It's in terms of man. So and then now we also have this, if the concentration of nitrogen gas is that, now they have already given us, no need of I even put the calculator away. They have already given us, remember their M there, the M is showing concentrations. So now is this system at equilibrium? So again, we find the Kc. So the nitrogen monoxide squared times the concentration of oxygen gas, and this is equal to, so for the nitrogen, monoxide, we have 0.0. We square this over nitrogen gas, so it's 2.00 times 10 times 10 power negative 4. So this is squared and then times. So for oxygen it is 0.00245. So we multiply this. We have 2 exponent negative 4. Multiply this by 0.00245, and that is what. So this is going to be 4.9 times 10 power negative 7. I hope you're able to see what I do. I always start with a complicated part. That's how I make life easy for myself. Okay, so work out the complicated part and put it in the formulas, then finish up everything. So 0.04 divided by 4.9 exponent negative 7 is going to give us, this is going to be 81,652.6. That will be the case. Now they ask the question to say, if at another temperature we have these values, does this represent a system at equilibrium? So the system is not at equilibrium. Why? Because the first value we found for Kc is more than the one that we have found. Unless they are equal, that's when you can say the system is at equilibrium. So we say system equilibrium. 408 meter 1000. So because they are not equal, so the system is not at equilibrium. Excellent. We go to the next page. This is now question 5. We have the equilibrium constant that is already given at 25 degrees Celsius. So at 25 degrees Celsius. Okay, so at 25 degrees Celsius, the equilibrium constant is 0.09, and this is the reaction here. Okay, so let me write the reaction properly. Gas, reversible reaction, air, gas. So now they ask us, which of the following sets of conditions is the system at equilibrium? For those which are not at equilibrium, which direction is the system going to shift? So the first reaction we have is this one, where this is the partial pressure of water. So let me just demonstrate how those have been written. They're supposed to be like this, ATM. That's how all the others should look like. Yeah, now they ask a question to say, is this at equilibrium? So remember that Kp we have put in front, so we're going to say Kp is going to be equal to what? So Kp is going to be equal to, so we use partial pressures because all these are partial pressures. So it's going to be from the reaction. From that reaction, we're going to say the partial pressure of L2 over the partial pressure of L2O. And here, all the partial pressures are given by 1. So it's 1 atm throughout. So this will be 1 squared over 1 times 1. Yeah, 1 times 1. And that's going to give us 1. So the Kp is just 1 there. Now the question is this at equilibrium? So if we compare with the Kp at 25 degrees Celsius, there it's 0.09, which is different from 1, because 1 is greater than that. So we can take that 0.09. We're going to say QC is 9 as our QC. So since 0.09 is less than 1, we're going to say QC is less than what? Kc. So since the system is not at equilibrium, we have to tell what's the direction, how is it going to shift. So shifting for this system, you look at where it's pointing. So this is pointing to the watches, to the KC. So, and this side, the way you're looking at it, obviously it's on your right hand side. So the system shifts to the right. It's going to shift to the right, or rather to the product side. So right. So that's how, in case maybe your QC was greater than KC, you say the system shifts to the left. So that's why you need to be starting with QC all the time instead of KC. So the first one they have given us is always the QC. So I remove this. That was just some supplementary notes. Okay, so we go to the next question. B, we're told to say we have partial pressure of water is 200 torr. So all these are given in torr. You may be tempted to start changing this to ATM. The thing is they are all in the same unit. So there's no need to change anything. You can just go there. Yeah, so here, what we are going to say, we're just going to say Kp is equal to the partial pressure of, so it's the partial pressure of a partial pressure of, so it's not into L squared, where we see H2O, partial pressure of Cl2. Okay, so which is going to be, so this is 21.0 squared over, we have 200 multiplied by partial pressure of this, which is 49.8. Okay. So what will this give us? So 249.8 is equal to that. So this is 9960, and then 21 squared is 441. So 441 divided by 9960 is 0.044. Now we go again to comparisons. So we know that 0.09 is greater than 0.04. So these are not equal. So again, here you say system at equilibrium. System is not at equilibrium. Since the system is not at equilibrium, how does it shift? So here our QC, because it's 0.09, so it's greater than what? KC, 0.044. That's what I mean. So that means it will shift left. So it's going to shift to left. Okay, so the last one I'll give you as an exercise again. I hope today you've done some more exercise, but I can send you even more questions if I want. Yeah, so but it's okay. You just have to do exercise. It's required for you to practice. But you may be thinking these things are easy, you find them tough in the paper. That's why we have to make sure that you take some practice. So pause this for 30 minutes, for 5 to 1 minute, for 1 minute, and then you see how you can go about it. And then you're going to compare your answer with the one that we'll find at the end. Okay, so this is going to be KC is equal to